SolidWorks Simulation Lecture 16, Flow Simulation, Part 5, Joule heating problems. For the first preparation step, we'll open the procedure and load the procedure flow simulation. And for the second preparation step, we'll open the toolbar. There are 5 toolbars for flow simulation. We only load the main toolbar, and this is the main toolbar. And for the first process of the simulation, we'll build a 3D model and open the case. And the procedure will prompt for lead creating, but this is for internal flow type, and we're running an external flow type, so we don't need to create any leads. And this is the end of step 1. And for step 2, we'll use the wizard to define the initial condition of the problem. And this is for the project name default. And we'll accept the default unit system. And we'll click on the external flow type with heat conduction and also with gravity. And we'll define the gravity on z direction. So this is the external flow type with heat conduction and gravity along z direction. And we'll choose the default fluid to be the air. And the default solid will be the nickel chrome metal. And the roughness is the perfect smooth. And the initial pressure would be the atmospheric pressure and ambient temperature of 20 degrees C. And these are the terms for external flow velocities, but I'll leave it at 0 because I'll simulate a stagnant air condition. So we'll look at the second step. We'll accept the default name and unit of the procedure and define the external flow type with heat conduction and gravity along z direction. And we'll choose the default fluid to be air, and default solid material will be nickel chrome, and then accept all the other defaults. And this is the end of step 2. And we'll also redefine the computational domain so that the z direction will be much higher. Positive z direction to be 3 meters high. So to simulate the real situation where the hot air will go upward. So this is the end of step 2. For step 3, we'll need to define boundary conditions for internal flow type, but this is an external flow type. But instead we'll define a current for the Joule heating problem. So we define current. Before we do that, we'll load the feature toolbar for flow simulation here, and we'll define the electrical condition and select the top surface and impose an in current of 10 amp, and also select the bottom surface and define an outward current of 10 amp. So for the third step, we defined a inflow current and outflow current of 10 amp. For step 4, the goals, we need to define global goals for example, voltage, the Joule heat, the total surface heat, static pressure, and also the velocity. And we also define the fluid temperature, total temperature, and also the solid temperature. And these are the global goals. And still we need to choose surface goal on the top and bottom surface, and maybe also on the cylindrical surfaces, so we can look at the temperature distribution on these surfaces. So I define the fluid temperature, the total temperature, and also the solid temperature of on these surfaces, so that the procedure will calculate the numerical value until it converges to a very small number. And so this is the end of step 4. And then step 5 will be the calculation phase. We'll hit the run button. And now we are in the calculation phase. And this is the iteration number. The iteration begins, and it is at about 5 iterations. And this is the result. The temperature distribution around the heatsink, the Joule heating component. And this is the total view. So you can see that the temperature buildup on the Joule heating component, because we pass a 10 amp current through the surfaces. And also the iteration is going on. It is about at 20th iteration. So I'll stop recording right now because it takes a little bit of time to complete the calculation. The software has finished, so we'll go back to the flow simulation interface and we'll look at the result. First of all, we insert a cut plot on the right surface, and we'll look at the temperature distribution on the cut plot. You can see the temperature distribution of the flow, but you do not see the solid part because it is not transparent. So we'll make the component transparent so we can see the inside. So this is the result. We can see that the temperature rises on the heatsink or the Joule heating component, and the hot air coming up. So this is the correct result. We can also play animation for this cut plot. And we can also see the flow simulation trajectory. We will insert a trajectory and choosing the top and bottom surfaces, and also the cylindrical surfaces, and look at the temperature distribution. So this is the flow line, and we can edit the flow line to be the vectors or arrows. And play animation. So you can see that the hot air going upward in the Z direction. So this is a proper result. And also we can look at the other components, for example, probing the temperature distribution on the surfaces. So this is the result for Lecture 16, Part 5, a Joule heating problem.